All right, so now we move on to part 2 of lesson 8.2, and that's the application of dealing with solving of systems of equations algebraically. So we've introduced the methods of substitution and elimination. In 8.1, we've talked about how we can graph these equations and then figure out certain intercepts. Now what we're going to do, or intercepts or solutions, I should say, now what we're going to do is take that one step further and talk about these things in algebraic applications, where we now have to model situations based on certain contexts given to us. Now, in example 1, let's take a quick look at the following. Two numbers are related. The sum of the first number and the square of the second is 18. The difference between the square of the second number and twice the first number is 12. Which of the systems below model this relationship? Now, what we got to be thinking about is the following. Let's try and match up that first sentence to one of the situations. So the sum of the first number and the square of the second is 18. Let's let that first number be x, and let's let that second number be y. Then if it's the sum of the first number and the square of the second, then that immediately rules out two of the following options. What we can do is we can put an x through number 3. Definitely cannot work, and I'm just going to use my straight line tool for this one. Does not work for this one. The other one that does not work is this one here. Reason being is because if you look at both these equations, it was the first number plus the square of the second. Well, 2 times y, or 2 times the second number, is not the square of the second, so we're going to eliminate that one. And it didn't say we add them together then square it. It said we add the first number plus the second number squared. So that's not going to be the right solution there. Now, that ruled it down so that it's a 50-50. We either have this one here or the one on the fourth system of equations. Now we go to our second sentence to see if either one of these fit our definition. The difference between the square of the second number and twice the first number is 12. Okay, so if our second number was equal to y, then we're looking for a squared on the y, which immediately rules out this equation here, because look at this. It's the first number squared, which was x. So that can't work. That's not the one that's going to follow here. That leaves us with the following. We have the fourth one, and before we highlight this and say, hey, this works, we need to be very aware of some little piece here that's within the equation here, or within the sentence, I should say. They say that the difference between the square of the second number and twice the first number is 12. They said specifically in that order that it's the square of the second number minus 2x, which was equal to 12. That was the indication they gave us, not that it was the other way around, because the order does matter in these sentences. When they say the difference between, and then they list a term and say the next one, they say this and this, they're telling you in a particular order. And because this one has the double number, or double the first number minus the second number squared, that's not the way they asked it. They asked it in the other order. Therefore, this also doesn't work. Actually, none of them work, which is kind of surprising that we're going to get a situation where none of them work, which, who knows? Maybe that is a possibility for us in terms of some sort of multiple choice, some sort of test question they might ask us is to reflect on these things and say, hey, maybe none of them are a solution. All right, let's go to example 2, where we're going to now build out equations based on sentences. So rather than just picking from ones that are listed, let's see if we can construct our own. So determine two whole numbers. Really important. We want to highlight that piece here. We're determining two whole numbers such that the first number increased by triple the second number is 24. Now, I always like to break these things sentence by sentence and create definitions. Let x be the first number, and then let y be the second number. I think it's really important to create a let statement right at the beginning, just so that you're aware of which variable equals what. Okay, now, according to this first sentence, the first number, which is x, is increased or added to the triple the second, x plus 3y, which is equal to, and if we put these things together, it supposedly equals 24. Boom, there's our first sentence. Now we go to our second sentence. If the first number is squared, so let's write that piece out. If the first number is squared and it's decreased, or there's a subtraction by 5 times itself, that means minus 5x, the result is equal to 13 less than the second number, meaning it's going to be y minus 13. Again, with that sentence, just to make sure it's clear, it said if we take the square of the first number minus 5 times the number itself equals the second number, which is y, minus 13. Find the two numbers. Okay, now Again, with this one, when we have a system, typically you would see a bracket out here indicating that these two are being compared to one another or that they're being collectively looked at together. Now, what we want to do is look at these and be like, we had two ways of solving these algebraically. I mean, graphically, we could plug them in as y equals and then solve. But if we want to do these algebraically, then we need to think about these things in terms of substitution or elimination. Now, before we do substitution elimination, what I would recommend is that we put all the variable terms on the left-hand sides of the equations, and then all the constant terms can stay on the right-hand side of the equation. And then eventually, we can bring them over. But I would say as we're doing potential elimination here, I would make sure they're all on one side. So let's just do that here. Let's say I have x and it's, just x plus 3y is equal to 24. If I bring that y across from the right-hand side of my second equation, over to the left, we're going to get that it is x squared minus 5x minus y is equal to negative 13. Now, in order to make these two equations have a common variable or something that we could eliminate, we got to think about it in terms of if we're trying to eliminate one of these variables, either the x's have to be the same or the y's have to be the same. And in this case, let's make the y's the same by multiplying this second equation by 3. So I recommend surround this all by 3, and we're going to rewrite out the following. It's going to be x plus 3y is equal to 24. We didn't adapt the first equation. The second equation is going to be 3x squared minus 5 times the x is going to, or 5 times 3 is negative 15x. And then minus 3y, because we're multiplying the y's by 3. And then on my constant term, 3 times 13, this is going to give me negative 36. Or negative 39, I should say, just to make sure we're multiplying everything by 3. Awesome. Okay, now if this ends up being my equation, here's what we need to be thinking. If these are opposite signs, 3 and the negative 3y, if they're opposite signs, you always want to add together the equations. And so when we add together the equations, the overall term will become, in this case, 0 plus 3x squared is 3x squared. We have x plus a negative 15x, that's minus 14x. Then we're going to go from here and say 3y plus a negative 3y is 0. And then lastly, equal 24 plus negative 39. This is the same as negative 15. All right, awesome. So here is our term once we've done our subtraction or elimination. Now I'm going to carry this forward up above, and I'm going to rewrite that term out again. It is 3x squared minus 14x. And then for our piece on the other side, it was equal to negative 15. I want this to equal some sort of trinomial so that we can either factor it, complete the square, or use the quad formula. So to do that, let's just add 15. Now, when we add 15 over, we're going to get 3x squared minus 14x plus 15, which is equal to 0. Now, we could quickly go through this in terms of like, hey, maybe we go right to quad formula from here and that's going to be what gets us the solution. The other thing we could do is think about this in terms of maybe it does factor really nicely. And so what I'm going to do is do the following, just to double check and see before I think to go to quad formula, because in this lesson you're going to see we use lots of quad formula. 3 times 15 is equal to 45. So we need to multiply to make 45, but then add to make negative 14. The numbers that we have available to us at this point would be, to multiply to make 45, it would be 9 and 5. And immediately, hey, look at that. We get 9 and 5, which come to mind. If I do this, I could go negative 9 and negative 5. Putting those together, you definitely add to make negative 14. And then multiplying them together, you definitely get your positive 45. So this might work for us. Now, again, in the case of this, we're going to see lots of quad formula moving forward. Quad formula might be your best friend in this section. For now, if you can factor it and these numbers seem reasonable and they're not decimals, I would try to factor first and foremost. Completing the square should be your absolute last. You should almost never rely on completing the square, only very specific applications. Now, what I'm going to do is now, because we need decomposition, I'm going to swap the negative 14 with the negative 9x minus 5x plus 15 is equal to 0. We know very well at this point from our quad equations unit that once we have it into this point here, or even from chapter 0, our factoring, we need to separate it into the two groupings. I'm going to remove out 3x, leaving me behind with x minus 3. I'm going to take out the negative 5, leaving me with x minus 3 in the other bracket. There we go. You know what I'm going to do? I'm just going to move this over just a tad because we're finding that it's kind of getting in the way of the problem here. So I'll move that up to about here. There we go. Now I could probably just write in these zeros just a tad better here. There we go, 0 and equals 0. Now I'm going to write the outside terms as one binomial and the inside terms as one binomial, or the shared terms as one, not the insides, but the shared term. Now that we have these two binomials, we're going to separate them and make them both equal to 0. 3x minus 5 equals 0. And then our other binomial will be x minus 3 is equal to 0. Awesome. To solve this algebraically, we're going to add 5 across, add 5 across. This gives us 3x is equal to 5. Lastly, we divide both sides by 3, and we get x is equal to 5 over 3. Now, our other one, simply put, we just need to add 3 to both sides. There's nothing to divide from x, so we get x is equal to 3. Now, let's just think about this for a second. When we zoom out on the overall problem, determine two whole numbers. Well, what does that mean? This root is actually extraneous. From class, we said that if it doesn't satisfy the contextual piece of the problem, then this is not to be considered, and we're going to write it as extraneous, or that it doesn't apply to the problem because we need whole number solutions here. So if we need a whole number solution, then we know x is equal to positive 3. That satisfies our one piece, but we still need the other number. To get the other number, plug this x equals 3 into either one of the original equations, and I always recommend doing the easier one, which is probably the linear equation in this case. So let's do that. To wrap up this problem, I'm just going to go over off to the side here, and we're going to take that original equation of x plus 3y equals 24. When I do this, it's going to be x plus, and let's write out the original. X plus 3y is equal to 24. I'm going to plug in my x, which is 3, plus 3y equals 24. When I subtract 3 from both sides, I'm going to end up getting that 3y is equal to 21. And then when I divide both sides by the 3 as such, I'm going to get that y is equal to 7. All right, now here's where you just want to provide a little bit of a sentence for this here. And what I'm going to do is just move this up just so that it doesn't cut into next problem. There we go. So if x equals 3 and y equals 7, that means that the two numbers or the solutions are going to be x equals 3 and y equals 7 are those two numbers that satisfy these two equations. Now again, what they might ask you to do is they might say verify this. To verify it, take these two numbers and plug them back into the original equations and make sure that your left-hand side equals your right-hand side. Secondary, make sure there's a sentence for this. I didn't put a sentence, but that's fine for the solutions in the case of we're just doing them in class, we're doing them quickly, we're getting these numbers. But if it's a written response, try to include a sentence just to make sure that your answer is very clear here. All right, now let's move on to example 3. Determine the values of m and n if there is a point 3 and 4 that is a solution to the following equation. Now, what we want to do is as soon as they give us a point, they're basically telling us that this is an ordered pair that satisfies both equations. If that is true, let's plug it in. What I'm going to do is I'm going to write this as m multiplied by the x value, which was 3, all squared, minus the n value, which was just n, we don't know it yet, times the 4, which is the y value, is equal to 32. Our second equation, we're going to get m 3 squared minus 5 times the y value, which was 4, is equal to n. Now, we're just going to take this another step in order to get these simplified. If I have m3 squared, well, this is the same as 9m. The other one is negative n4. This is 4n, and then which is equal to 32. For my second equation, again, it's going to be 9m, and then I have the negative 5 times 4 is negative 20, which is equal to the n on the other side. There we go. So we've now reworked our system such that we've plugged in the x and y that satisfies for both. Now what I want to do is I want to use substitution. And the reason I'm going to say use substitution is because, hey, look at this. We already have one of the variables n isolated. So what we're going to do is we're going to take all of this, that 9m minus 20, and then just plug it in for the n in the first equation. So let's do that off to the side here. We're going to continue by doing this. It's going to be 9m and then minus 4n, but instead of n, we're going to plug in 9m minus 20, and then this is all equal to the 32 from the original equation. Awesome. Now I'm going to expand this. This is 9m. 9 times 4 gives us negative 36m. 4 times 20, both negative, gives us positive 80, which is equal to 32. Now from here, I'm going to simplify this and say, well, 9 minus 36, we're going to get this as negative 27m. If I subtract 80 over to the other side, this is 32 minus 80, just as a way to make sure that we're getting values fast here. 32 minus 80 without mistakes, we're getting negative 48. There we go. We divide both sides by the 27. So negative 27, because we want that m alone. This is going to give us m is equal to, whoops, there we go. M is equal to, well, 48 over 27, we can actually divide these both by 3. The negatives cancel. This becomes 16 over 9. There we go. So here's the m value, or the value of m that would satisfy for both equations. In order to solve for the n, what we're going to do is, because we use the substitution method, let's just take this m and plug it back in for the second equation such that we can just solve it. Or I should be pointing over here because this was our more simplified form. If we know n is isolated in this equation, then plugging in the m is going to allow us to solve for that n. So let's do that maybe on the right-hand side, just where, no, I'm going to say right below. I think this is going to be more room for us. So first and foremost, we have our 9m, which in this case, yeah, let's substitute in the 16 over 9 right away. So 16 over 9, close the bracket. Our next term was minus 20 is equal to m. 9 over 9 is just simply 1. So the 9s actually will both cancel here, 9 over 9. We're given 16 minus 20 is equal to m, or in this case, n. Yeah, we don't want to make that mistake. There we go. And therefore, we get an n value, which is equal to negative 4. Awesome. So this is that secondary value, or the other value that satisfies this equation. Now, again, we could verify this if they ever asked right at the end or the tail end of this problem, like perhaps they say, hey, I need you to verify that this is what actually happens, or that the m and the n are the actual values for this. Take both of these two values and plug them into the original and see if the left-hand side equals the right-hand side. Now, for the notes that will appear online, what I'm going to do is I'm just going to shift all of this up just so that it's not so crammed against the bottom there. And then that should look a touch better here. And what I'm going to do as well is I'm just going to arrow over, indicating that we went from these equations to then isolating for our m value from there. All right. Now, let's go to our next part here. So if we want to solve a problem involving linear and quadratic systems, they may give us some sort of word problem, just as we've seen before in quad functions, quad equations. This is no different, just a little more applied in terms of we're now going to have to figure out, based on two quadratic equations or functions, what is a solution, or what is the intersection between these two. So first and foremost, a Canadian cargo plane drops a crate of emergency supplies to aid workers on the ground. The crate drops freely at first, before a parachute opens, to bring the crate gently to the ground. The crate's height in h, which is in meters, above the ground t seconds after leaving the aircraft, is given by the following two equations. The first equation is the height of the crate just in free fall. It's dropped to the plane, it's falling to the ground. It's modeled by this first equation here. h1 equals negative 4.9 t squared plus 900. The second equation is the equation that represents the piece at which it falls with the parachute, or the height at which the crate with the parachute will be falling. All right, now, how long after the crate leaves the aircraft will the parachute open? Here's how we're going to solve this. Algebraically, we're going to either use substitution or elimination, and elimination might be our best method, but let's just see that in a second. What I'm going to do is I'm going to look at this and be like, if we want to visualize this just for half a second, if you drew out a basic Cartesian plane such as this, and maybe we actually just draw this in, why not? So if I have something like this and like this, well, the overall situation of the problem is going to be that we have a y-intercept at 900 and one at 500. So we're going to have something like this here, and maybe I'll put a dot here. So here's our y-intercept at 500. Here's our y-intercept at 900. Now, the parabola is coming down from the 900. So it kind of like shoots out from here and then makes its way to the ground as such. And then our linear line, which is our 500, is going to be some line that kind of cuts across and has this negative slope and meets about here. Now, We could probably do a little bit better of a drawing than this. What I'm going to do is I'm going to make this kind of go up just a tad and then put the line over. So from here, our line that would represent the parachutes graph might look something like that. Now, what we're actually looking for on this is we're looking for the piece at which they intersect, because if we know this piece here, this intersection, it is the height in which the parachute is pulled, because anywhere past here, now it's the parachute that's taking the work to the ground. So we need to figure out what is this intersection in terms of height and time in which the free falling item matches the height of which the parachute would pull. Okay, now let's erase this out and we're going to do this algebraically. Now, again, like I said before, algebraically, what we're going to focus on is now using quadratic formula because it's such a powerful tool. And when they say solve algebraically and there's decimals involved, what you're going to want to do is immediately go to quad formula. First and foremost, we must do our elimination. So let's write these out. H of t, or the first h of t, is equal to negative 4.9 t squared plus 900. We then have our second h of t, which is equal to the negative 4, and it's just a t, and I'm just going to make sure there's no decimal. Yeah, perfect. There we go. Okay, now if we want to eliminate the height variable such that we can solve for the time, right? Because they said for how long after the parachute open, we want to figure out what is the time it takes to pull the parachute, or how long it's in the air before that parachute is pulled. Now, if I eliminate these, we know that the h of t's are the same. If they're the same and the same sign, we're going to subtract, just like we've said in the previous sections. This will mean 0 is equal to, we have negative 4.9 t squared, and then 0 minus 4t, this is actually plus 4t, and then 900 minus 500 is plus 400. Okay, now from here, we're going to establish an ABC, right? Because as soon as you see a decimal, you're like, okay, maybe quad formula is going to be our best method. So we have negative 4.9 for our A value. We have our B value, which is equal to positive 4. And then we have our C value, which is equal to positive 400. And these are all just the coefficients or the constant terms that are within the quadratic equation we've just established with elimination. Now from here, we're going to plug it into the quad formula. X is equal to the negative B value, which is 4, plus or minus the square root of B squared, which is 4 squared, minus 4 times the A value, which is 4.9, or negative 4.9, times the C value, which is positive 400, and then all divided by 2 times the A value, which is negative 4.9. There we go. Now let's simplify this in the calculator. So I'm going to pull that up off to the side here. If I type this in, I'm going to get, first and foremost, let's simplify the radical. So everything else we're going to keep the same. I just want to see what this radicand becomes, or the part under the radical. 4 squared minus 4 times negative 4.9 times 400. This should give us a larger positive value, and we're just going to bring it off to the side here. So this is going to give us 7,856. So plus minus 7,856, all divided by 2 times 4.9. 2 times 4.9 will give us the 9.8, and it's going to be negative. There we go. Now we're going to have two following situations. One situation is the positive case, the other one is the negative. So let's make sure we write both of these out. X is equal to negative 4, positive case first and foremost, 7,856, all over the negative 9.8. And then in terms of our other X value, we're going to use the negative case. So let's first of all, actually, I think it makes sense to just evaluate them one at a time in the fraction. So we're going to go math frac, negative 4 plus the square root of the 7,856 divided by the negative 9.8. This is going to give us negative, negative 8.63 and this is in seconds. Now for our other one, let's make sure we write it out here. Our other case scenario was when X is equal to, we had negative 4 plus, or no, in this case it's the minus 7,856 divided by the negative 9.8, which is going to give us an X value of, we take the exact same thing as above, we're just going to swap the sign here. So I'm going to go up, whoops, that might be a little too much. There we go. Delete that out here. well, we want to keep that negative, but we want to delete out our positive and make it negative. This is going to give us 9.45, and there is a decimal of 2 after. Okay, now let's reflect on this problem here. What did they specifically ask for? Solve algebraically to the nearest hundredth, or the second decimal place. So if we're looking for the second decimal place, then we're going to round these to 2 decimal places. And what I'm going to do is I first of all got to reflect on this and be like, which of these is extraneous? If you get a negative amount of time, clearly that's not going to satisfy the problem. So what I want you to do is circle it, line through it, put ext, representing that this is the extraneous solution. The solution we're interested in is this solution here, the 9.45 seconds. And we're just going to make a quick sentence about this because, again, if it's a word problem, try to wrap it up with a sentence. So the time the crate, and specifically, I just want to reflect on it from the sentence, for how long after the crate leaves the aircraft does the parachute open? The time it takes for the parachute to open is 9.45 seconds. There it is. And just to make sure we have the right solution there, perfect, excellent. We're just going to make sure we highlight this all, indicating that we have the total solution here. There we go. And maybe I'll just lower this just so that it's closer to where we actually got the root and that people aren't confused by how this came about. Perfect. Okay, again, quad formula is going to be your best friend in these problems. I'm telling you right now, as soon as you see decimals, you should be like, quad formula is going to be where I go. Because if you do the complete the square and then square root principle, or even the factoring method on decimals is brutal. Unless you can make them all whole numbers, but then they're going to be really large. Trust me, just go with the quadratic formula and you're going to be happy with these. All right, part B. What height above the ground is the crate when the parachute opens? Well, simply put, all we need to do is take this time and then plug it into the formula. So to do that, we can plug it into either one. Again, I always choose the simpler equation. It doesn't really matter which one, but the linear equation tends to be the more simple one. If they're both quadratics, just plug them into one. But I'm going to take that linear system, or the linear equation, and write, well, the height at the specific time, which was 9.45, this is going to be equal to -4 times that 9.45 seconds, and then plus the 500, which was its starting height, or the starting intercept for this, because technically the parachute doesn't have a height, it's just the parachute's function. Okay, from here, this is going to be equal to, if we plug this into our calculator, we are going to get -4 times, make sure that's a -4, times 9.45, and then we're going to add 500. This means at a height of 462.2. And to the nearest meter, this would be 462 exactly. So 462 meters is when the parachute opens, and we're going to summarize it as that. At 462 meters, the parachute opens. Perfect, there we go. And we'll highlight both of these together, representing that that's our solution we want. And then verify this solution graphically. All they're gonna do is ask us to type in these as H functions into our graphing calculators. Now, just so that you're aware again, H or any sort of thing they describe in terms of a height and time as a function. So we have a function of height in relation to time. These are just another way of saying y. It's just like when we write f of x equals y, h of t's are equal to y. So I'm just going to rephrase both of these equations, but in terms of y, so that we can type them into our graphing calculator. So we're going to get y1 is equal to -4.9. Instead of t squared, I'm going to write x squared plus the 900. For my y2 that I'm going to type into my graphing calculator, I'm going to type in -4x instead of t, and then plus 500. Now, let's see if we can generate a rough sketch based on this situation here. I'm even going to put the axis points off to the side here. And anytime there's application, think about this as in terms of it will most likely be describing quadrant 1. The reason being is because time is never going to be some sort of like negative value in here. So I would highly recommend you keep it in terms of leave it for quadrant one, or make a graph that's of quadrant one. Now in here, we're going to go y equals, and we're going to type both of them in here. So starting with the first one, negative 4.9 x squared plus 900, which was the first function. Second function was negative 4x plus 500. This gives us this graph. We don't see anything. We're going to have to adjust our windows. Y max, because it goes up to about 900 or above, let's make it 1,000. Your X maximum, let's say because our times were about 9.45 for where it met, I'm going to make that time about like 15 just to really extend it out. I'm going to make my X minimum something like -2 because we don't really need to see much of the negative X's or the negative times because that's not a thing. The Y minimum, -10, that will be more than enough. Perfect. Here's a graph that works for us. So I'm going to sketch this in here and maybe I'll see if I can do this together here. I'm going to have to hide it in a second. So what I'm going to do is I'm going to sketch down the line. The blue line, or the red line, is going to be our linear. The blue line is the quadratic. So let's do that here. Here's kind of the rough shape. Extend it out this way and then crash down. And then our red graph, which is our linear line, I know it looks pretty horizontal, but that might just be the way our window is. It's going to be from 500 and then across and meet somewhere there. So let's just say that this generally represents that. Perfect. And then here is that intersection point. Graphically, if we want to solve this, here's what we're going to do. If you have the Casio, you're going to go Shift, G solve intersection. For TIs, we're going to go Shift, trace, intersect, and then we're going to go left bound, right bound. For you, you just need to go over the point and click enter 3 times. We find that that intersection is 9.45 and 462. Exactly the solution that we got for this. So this was at 9.45, and for the height value, this was 462 to the nearest meter. There we go. Perfect. And then what we could do is we could even sketch it like this is a specific time. And then if I did my horizontal line over across that point, it would look something like there. There we go. And then you could say like this is 9.45 down here, and that this is 462 over here. Now, obviously that's a little extra, but that works for us. And then just so that you're aware of the window settings, just in case. So for our window settings, let's bring it back up again. Our X minimum we said was -2. Our maximum we set to 15 because it's not going to take longer than that 15 seconds if one of our interception points is at 9. And then our scale is 1. We try to keep it as 1 as much as possible. In terms of the Y's, let's see if we can swap it over to this side. I'm going to go Y. For my first piece, it's going to be -10. Again, we could have adjusted that so it was a little higher, but we didn't. 1,000 because our highest point, it left the plane at 900, so I just went a little above. And then the scale factor, I just leave as 1. I mean, we could adjust that if we wanted to, but I didn't really feel like adjusting it. Awesome. Okay, there's our graphic solution. That goes back to 8.1, which is the graphing section. Remember, we need to have them in terms of y equals for both of them, or else this doesn't work. And just like f of x, h of t is also equal to y. Okay, let's go to our next page here. We have the following situation. Terry makes a good hit in baseball, and it travels on a path modeled by h of x equals 0.1 x squared plus 2x. Ruth is an outfielder directly in line with the path of the ball. So it's getting hit, it's following this parabolic shape, it's coming back down to the ground, and then Ruth is there to catch the ball. She runs towards the ball and then jumps at it to catch it. Her jump is modeled by h of x equals -x squared plus 39x minus 378. If both of the equations have the x being the horizontal distance in meters from the home plate and h is the height of the ball above the ground at any given point, then solve this system algebraically for where Ruth catches the ball that Terry hits. Okay, now a prime example again of one that you're going to want to use quad formula for. As soon as you start seeing decimals like this, it's like, whoa, this is going to be a lot to deal with unless we can simplify it. So let's write these out together as a system of equations. First and foremost, we're going to write h of x is equal to, and we're going to write Terry's function for her hit. It was -0.1, and then I'm going to keep it as x squared plus 2x. All right. Now for Ruth's hit, or for Ruth's catch, I should say, because she's not the hitter, Terry's the hitter. For Ruth's catch, we're going to write this as -x squared plus 39x, and then minus 378. Okay, ideally, what's going to be best here is probably elimination. Now, the reason I say elimination in these problems is because I guess we could do substitution, which would just simply mean that this equation equals this equation, and you could isolate across. But in this one, if I can vertically stack them like this and say that this is the system I'm looking at, then algebraically, let's just take these and subtract them, because then we can get rid of h of x over h of x. This is h of x minus h of x, which is zeros. Perfect, which is equal to negative 0.1 minus minus 1x. This is the same as saying we're taking negative 0.1 and then adding 1. This is going to give us 0.9x squared. We have 2x minus 39x is minus 37x. And then 0 minus this constant, because technically I guess you could write a positive 0 for here. 0 minus the negative 378 is positive 378. All right, again, this is exactly why you want to go into quad formula, because this might be super overwhelming if you don't use quad formula. You're going to try and like do the complete the square and then square root principle or factor this thing. I don't think so. I would just go right to the quad formula. A is 0.9, B is negative 37, C is equal to 378. And let's just double check signs, because I think that's always a good idea. Yeah, first equation minus second equation, we get positive, negative, positive. Okay, awesome. Now let's go into our quad formula. It's going to be x is equal to negative b value, which is negative 37, plus or minus inside the bracket here. We are going to write this as negative 37 all squared minus 4 times 0.9 times 378, all divided by 2 times the a value, which in this case is 0.9. Awesome. Now x is equal to, the negative negative becomes positive 37, plus or minus the square root of. In our calculator, let's actually do this one together. If we take this, it's going to be 37 squared. Again, oh, whoops, I'm in the window mode. That's not going to help us. I'm going to take the 37 and just square it as is. The reason I am is because a negative squared is positive, minus 4 times 0.9 times 378, done. This is going to give us 8.2 under the radical, so I'm going to put in 8.2 and then just kind of wipe out the rest of that radical that I don't need. This will all be divided by the 1.8 in the denominator. There we go, because 2 times 0.9 gives us 1.8. And just to even show you there, so we have it, there you go. Now, when we look at this, we're going to separate it into the two cases here. First case, x is equal to 37 plus the square root of 8.2, all divided by 1.8. What I'm going to then do is just actually calculate this value here for us. So we're going to type in exactly what we see here. Fraction, most of you have the fraction key. 37 plus the square root of 8.2 divided by 1.8. This will give us 22.146. And I'm just going to hold on to a couple decimal places for now. My second one is going to be x is equal to 37 minus the square root of 8.2, because we got to do our plus and minus case. And the reason I'm erasing that is just to make it a touch neater. There we go, 1.8. This is going to be equal to, in our calculator, we can just copy back that same piece. Casio's and TI's both do that function very well. I'm just going to swap out a positive for a negative here, and this is going to become 18.964. There we go. Okay, now zooming back on the problem here, we just want to be looking for the context clues as to what is going to help us here. So rounding to the nearest hundredth, we want these to the second decimal place. They say determine which height it would be in terms of meters above the ground for where this is caught. Now, something that is a little bit surprising here is that I feel like we're getting a fairly large value here. So let's just double check our values here. Because we want to figure out in both equations, x is the horizontal distance. Actually, no, this works. This is good for us. So I was just confusing the height and the x. So that's where my mind was kind of going to. I was like, these seem very large, but it's because this is the horizontal distance away from home plate. Both of these seem pretty reasonable. Actually, on surface value, 22.146 meters or 18.96 meters, both of these seem okay. That's not what they asked us for, though. They said, we need to solve this algebraically such that we have a distance from home plate and we have the height. Because right now, all we have is how far it went. We don't really have the y value or the h value. So to figure that out, it's actually quite simple. For part two, we're going to bring it up here and we're going to plug it into the functions. And it can go into either one of these because supposedly at those distances, the height should be the same for both the ball and the person catching it, aka Terry's hit will be landing in Ruth's glove at that given height at that specific distance. So let's maybe plug it into the more simple equation, which I deem is the first one. Okay, if I type this in, it's going to be the following. We're going to get h of the 22 point, and I want to hold on to as many decimals as I can, 146, which is equal to 0.1 and negative 0.1, just to be more specific. And I'm feeling like I'm going to need to move this over just a tad. This will be negative 0.1 times 22.146 all squared, and then plus 2 times the 22.146. There we go. This is going to give us a height at the distance of 122.46, 146 that is, equal to, in our calculators, if we type this in, we go negative 0.1 bracket 22.146, whoops, negative 0.1 times in brackets 22.146 all squared, and then plus 2 times 22.146. This will be equal to negative 4.75. Now, that's clearly not right. I mean, we're getting a value that's negative for height. Whoops, that doesn't work. So if that's equal to negative 4.75 meters, immediately, I mean, we could call this extraneous, but let's just solve our other one and then we'll also mark the other one depending on what happens. So for our second case, it's going to be height at 18 point, we're going to go down here, 964, close the bracket, is equal to 0.1, 18, oops, there we go, 18.964 all squared plus 2 times 18.964. There we go. This gives us a height of 18.964, or sorry, a distance of 18.64, where the height is. In this equation, we're just going to now type in instead 0.1 times 18.964 all squared. We're going to then add 2 times the 18.964, close the bracket, and we get 1.96 meters. Awesome. Okay, here's the possible two solutions that we got from here. And so based on these solutions, or based on the fact that these are solutions, what we can now do is go below and be like, the ordered pairs, therefore, we have where our height was, or a distance away, our x value was 22.15. I'm going to round it to the nearest hundredth, and negative 4.75. Or we have, or, there we go, we're going to have our 18.96 and our 1.96. Now, clearly, there's only one solution in this case because the other one is going to be extraneous. So we're going to circle that one, put a line through it, put ext representing that this solution cannot exist because they're not going to go traveling below the field or into the ground. That doesn't make sense for them. So therefore, the only solution out of here would be that the person, specifically that the solution is where they have 18.96 as the distance away from home plate, and then 1.96 meters is how high that Ruth catches it above the ground. All right, now going below, explain the meaning of the point of the intersection. Simply put, exactly what we just said. And I'm not even going to use the names here because Ruth is the catcher. Ruth catches the ball. 18.96 meters away from home plate. And, whoops, there we go. And jumps And wait, and I guess we could pair it together in this way. Ruth catches the ball 18.96 meters away from home plate and 1.96 meters in the air. That will be the easiest way to wrap up the problem there. There we go. We'll highlight it just to represent that this is the sentence that pairs with our answer here. Awesome. Okay, here's where you're going to want to go into your assignment with these. Again, when you're solving an 8.2 part 2 or problems that involve this contextual piece with decimals and all this other stuff, use the substitution or elimination methods we talked or told you about or we've instructed you through. But then I want you thinking, okay, once I use that substitution or elimination, now I must be primarily using quadratic formula because if you try to factor or complete the square with these decimals, you're going to be spending so much time, way more time than you need to on these things. In fact, it would take you hours sometimes, depending on the specific problem, to either factor or do the complete the square method. And you don't want to be set up for failure on these things. So what I would say is anytime you face these types of problems that we've went through today, factor them if the numbers are easy enough, such as natural numbers or integer values. If they're not integer values, just go right to quad formula.